4.1. 4.1 is basic concepts of probability. So, 4.1, basic concepts of probability. Basic concepts of probability. Okay, so example number 1. If you look at example number 1 is really actually, it's kind of simple, but it's also very important that you understand this process. Understand what's going on in example number 1. Because this is going to be kind of the bedrock of what we do from now on. Okay, we're going to do several different kinds of testing. We're going to test for the probability, we're going to test for means, and we're going to test for all these different things, but it's based on the concepts on example number 1. So as you're reading example number 1, I want you to kind of think of how this compares to, remember we talked about the guy who says he's 90% free throw shooter, and we talked about this guy, right? So kind of think about that as we're talking about this example, okay? So example number 1, claim we have developed a gender selection method that greatly increases the likelihood of having a baby girl. Okay. Well, this would be magic, right? Nobody's been able to do this before. So the hypothesis is used when testing the claim is the method of the gender selection has no effect, so that for couples using this method, about 50% of the births results in girls. Okay, so the hypothesis, as you can tell, the hypothesis is what you're trying to disprove, right? This company is trying to disprove this, correct? They're saying that they have this magic thing that'll make you have baby girls, right? So you're trying to disprove the fact that you're going to get 50-50 chance, which is the random selection where it's supposed to be, right? Boys and girls, okay? Flip the page. Let's look at that little flow chart there. If you flip the page. Okay, so different gender selection method is tested with 100 births. So if you take 100 births, right, and you got 75 girls and 25 boys. Now that's something, right? Obviously something's going on here, right? Because normally you would have 50 and 50 or somewhere around there, right? 52, 48 or something, right? So when they did the calculations, the probability of them having, if it was 50-50, the probability of having 75 girls and 25 boys is 0.0000003. 3 in 10 million. Wow. This is statistically significant, right? Definitely less than 5%, right? Definitely something's going on here, right? Okay. The test B result. In the test B, we did it, and they got 55 girls and 45 boys. What? More girls than you would think, but is it still within the realm of 50% chance?
Yeah.
Okay, so this is what they're saying. So if I had, again, if I had 50% chance, the chances of me getting 55 girls and 45 boys happens to be 0.184. In other words, 18.4%. So, based upon what we've learned so far, is this statistically significant? No, it's not, right? As Fabian says, it is not. It's definitely not because it is greater than 5%. Right? Remember, we agreed that 5% was the cutoff. Okay? So this would basically be a lucky or unlucky draw, right? Okay? Whereas the other one is not a lucky draw. You do not get 3 out of 10 million lucky. Okay? Right? You still wouldn't be able to win the Powerball, but I mean, that's still something. Okay? Does anybody know what the odds of hitting the Powerball is? No, I think it's like 170 million. I think 1 in 170 million or something like that. Or some ungodly number. To the point where, the saying is, the chance of you winning the Powerball is just about the same whether you buy a ticket or not.
Well, we better just go look.
Too bad you can't, or can you?
Maybe.
Don't you have to be
So I'm
It's
going.
18.
18, right?
I can test my luck.
Oh, Jesus.
Okay, so again, look at that flow chart. Let's look at the 75 girls, 25 boys, right? Chance rejected as a relationship. So chance, in other words, lucky or unlucky draw, right? It's not by chance that this happened. Not by chance that you get this thing that only happens 3 out of 10 million times. Okay? So in other words, there is something going on there. The gender selection method appears to be effective. And this is how you would prove or disprove a probability or something. Okay? This is the logic that we're going to use from now on. Okay? On the other one, look at what do you have? Chance not rejected as reasonable answers. In other words, okay, we cannot conclude that the gender selection method was effective. We're just having a bad draw. And, okay, that's what they're saying here. And this is how you reject, or you never accept. You either reject or you fail to reject. Okay? Right, we'll talk about this in greater length later on. But you never accept, you either reject or you fail to reject. Okay? All right? Okay. That's good. Now let's go on the bottom. It says, basics of probability. And there are 3 definitions there. Read it for us, please.
Sorry,
I picked the one person who didn't have the book.
which one is it?
The definitions, the orange box on the bottom of page 134.
An event is a collection of results or outcomes of a procedure. Do you want to read the next one too?
Please.
A simple event is an outcome or an event that cannot be further broken down into simpler components. The sample space for a procedure consists of all possible simple events. That is, the sample space consists of all outcomes that can be broken down any further.
Okay, thanks. Okay, so, an example 2, it shows you the event, the simple event, the sample space of what we were talking about, the boy-girl thing, right? Okay? So there's a boy-girl thing, and if we had 3 births, right, there are 3 births, we could have what? We could have boy, boy, boy. If I had 1 girl, it could be either girl, boy, 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 girl, boy, or boy, boy, girl, right? Or I could have 1 boy, right? It would be boy, girl, 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 boy, girl, 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 boy, or I could have all girls, right? 1, 2, 3, 4, 5, 6, 7, 8, which makes sense, right? Because each baby has 2 different kinds of probability, right? I had 1 baby, 2 babies. We're talking about 3 babies here, right? 2 times 2 times 2 is 8. 8 different possibilities here, right? So the probability of me having 1 boy is what? Out of the 8, how many ones have 1 boy? It would be 1, 2, 3, right? 3 out of 8. What is the probability of me having at least 1 boy? Which one has at least 1 boy?
7 out of 8.
All of them, but
And the last one.
all of them, but all girls.
Okay. Did you hear what she said? Okay, so you guys are, okay, everybody else is saying, okay, let's see, the top 7, all of them have boys, right? So it's 7 over 8, right?
Mm-hmm.
Which is perfectly fine. That's a good way to calculate it, right? But the other one was that instead of counting how many have at least 1 boys, I'm going to just find out how many do not have a single boy. And that's just this one right here. So 1 minus 1/8, 1/8 right here, right? Equals 7/8, the same thing. Okay? different way to think of it, same result. Okay, all right, but this will come up later on. Okay, thinking about it this way. All right, so I want you to kind of think about that. Okay, we're good there. Blah 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 blah. 3 common approaches to finding the probability of event. What the heck is this? Okay, so notation for probability. So notation, let's talk about that. Probability of me, for this one, having a boy. Okay? Probability of me having, so this would be, I don't know, we would probably say something like 1 boy. 1 boy. Right? Probability of having 1 boy. Okay? And we could calculate it, right? But this is just the notation itself. Okay? We will also learn a different one, like we will learn something like this. And we'll talk about this later on, but as of now, you don't have to know that. Okay. So that's how you denote the probability. Okay. And how to calculate it, we already talked about. You look at the entire sample space and find out how many events qualify as what we were actually looking for, right? Okay. Subjective probabilities. Classical approach, we just talked about that. We're good with that. Subjective probabilities. We're on page 136, by the way. P of A, the probability of event A is estimated by using knowledge of the relevant circumstances. I have no idea what they're talking about here. Here we go, wait a minute. When trying to estimate the probability of getting stuck in the next elevator that you ride, we know from personal experience that the probability is quite small. Okay, I still don't know what they're talking about. Don't worry about it. If I don't understand it, you don't have to understand. Simulations, top of page 137. Okay, top of page 137 has simulations. Simulations is something that we run on a computer normally, right? We normally run on a computer and we try to model certain events, okay? So let's say I was trying to figure out whether I'm going to get a head or a tail, right? If I'm going to get a head or a tail when I flip a coin, right? I would model that, and instead of taking a coin out and actually doing this 500 times, right, I could use a computer that would randomly generate numbers between 1 and 2, right? 1 would be head, 2 would be tail, and I would just have them just do a random thing, and I could count it right there, right? Instead of me actually having to flip it. Right? We'll talk about that later on as we go, so don't worry too much about that. The orange box, law of large numbers, law of large numbers. So this is, again, when let's say that we're flipping a coin. If I flip a coin 10 times, how many times am I going to get heads? 8? Well, okay. Well, so we theoretically know that we should get 5, right? Out of the 10 times, it's going to be heads. It should be, but you're not guaranteed. Like Fabian said, you could get 8, right? Who knows, right? So this is what we call empirical data, or this is basically, or it is not the theoretical value, right? So how many times do you think it would take us to actually, so as I continue to do this, right? The law of large numbers says that as the number of trials get big, I get closer and closer to the theoretical probability, right? In other words, I kind of iron out all these little blips or blimps or whatever you would have, okay? All right. That's what the law of large numbers means. As a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability, okay? That's what they're saying there. Anybody want to hazard a guess as to how many times it would take for a coin flip to to actually really, truly approach 50%? How many times do you think it would take? How many times do you think we'd have to get to do that?
Can you repeat the question?
So the question is, so if I'm flipping a coin, right? Like you said, we're not guaranteed to get 5 times out of 10. We're not guaranteed to get 50 out of 100, right? But as you go further and further out, somewhere down the line, it all kind of irons out to 50%, right? So how many times do you think? Oh, I'll let you guys research that. Okay, that'll be extra credit for the homework. 25 is incorrect. Nice try. Okay, so then we have example 3, 4, and 5. I'm not going to go through that. I'll let you guys read that. There really isn't anything that's interesting there. And when we come back tomorrow, we will do the complementary events. Okay, so what did we learn today? Probability. Okay, we learned. Okay, so again, really what was important was that example number 1. Okay, example number 1, following that logic. Okay, this was kind of nice. The notation was kind of nice. This was kind of nice too. Okay, all right.